So, what if I told you that the mountains you see, the ones that seem so permanent and strong, are actually slowly and silently falling apart? I mean, we think of them as these timeless symbols, right? But they are in a constant battle with invisible forces, forces that work day and night to tear them down and turn solid rock into, well, something much more dangerous. And this is what that raw power looks like when it's unleashed. You're looking at Caracas, Venezuela, back in December 1999. After days of just relentless, almost biblical rain, the mountainsides above the city just let go. This wasn't just a flood. It was a liquid avalanche of mud, rock, and trees that just swallowed whole neighborhoods. It tossed cars and buildings around like they were toys. I mean, it's a really terrifying thought, isn't it? How does something that we see as the definition of solid, a mountain, suddenly liquefy and just wipe out a town? Well, the answer, as we're about to find out, is a story that begins way, way before the first raindrop ever falls. It's a story of slow, silent sabotage. See, the secret is that these disasters are almost never truly sudden. They're actually the final, really dramatic act of a very long, very slow process. It's like a kind of sabotage that weakens the mountain from the inside. And that whole process, it's called weathering. So to put it simply, weathering is just nature's way of breaking big rocks down into smaller bits and pieces. It's the absolutely crucial first step. Before a mountain can collapse, it first has to be weakened, cracked, and basically rotted from the inside out. Weathering is what sets the stage for everything that comes next. Okay, so let's dive into this silent sabotage. There are two main ways that nature wages this war on rock. And first up is what we call physical weathering. You can think of this as the brute force method. It's all about literally physically breaking rock apart without actually changing what it's made of. You know, the key to any attack is finding a weakness. And guess what? Nearly all rocks have them. We call these weaknesses joints. Think of them like the natural cracks in a suit of armor. They're these pre-existing weak spots that let water and other forces get deep inside the rock, which is, of course, where they can do the most damage. So where do these cracks even come from? Well, a big one is a process called unloading. Just imagine a rock that was formed super deep underground, right? It's under immense pressure from miles of other rock piled on top of it. Well, as erosion slowly removes all that weight from above, the rock down below starts to expand. And just like a compressed sponge, when you let it go, it cracks and it fractures. And this is what those joints actually look like out in the real world. Over on the left, you're seeing these sheet-like fractures. It's called exfoliation, where the rock literally peels away in layers, kind of like an onion. Then on the right, in a totally different kind of rock, the joints are way more blocky and angular. The way a rock breaks really just depends on what it's made of and the forces that are acting on it. Okay, so we're breaking big rocks into slightly smaller rocks. You might be thinking, what's the big deal? But this is where the real magic of weathering starts to happen. So let me ask you, why do these tiny little cracks matter so much when you're talking about taking down an entire mountain? Well, let's think about it with a super simple cube. Imagine a solid block of rock, 2 centimeters on each side. If you do a little bit of quick math, you'll find its total surface area, that's the part that's actually exposed to the elements, is 24 square centimeters. And here is the absolute kicker. Now, what happens if we break that one cube into 8 smaller pieces? The amount of rock is the same, but the surface area, it just doubled to 48 square centimeters. Every single new crack exposes fresh rock, and this dramatically increases the area where that second type of weathering can get to work. So physical weathering has just opened up this massive new front for an attack. And now it's time for the second, and I'd say more insidious, form of weathering to get going: the chemical takedown. Yeah, if physical weathering is the brute force, this is the covert chemical assault. It doesn't just break the rock, it actually changes what it's made of, dissolving it from the inside out. A really key process here is called hydrolysis. Now, I know it sounds super complex, but the idea is actually pretty simple. Water's not just sitting there. Its molecules are chemically reacting with the minerals inside the rock. And the result? A total transformation. Strong interlocking crystals of a mineral like feldspar are literally broken down and converted into soft, weak clay. You're basically watching the rock's solid skeleton just rot away. And what's really fascinating is that not all minerals are created equal in this chemical war. Take limestone, for example. It's made of calcite, which has pretty weak chemical bonds, so it dissolves relatively easily in rainwater. But then you have quartz, the main ingredient in sandstone, which has these incredibly strong bonds. It's way more resistant. And this is exactly why you see these huge cave systems in limestone areas, but then you see towering, resistant cliffs of sandstone somewhere else. So after millions of years of this chemical assaults, what are we actually left with? Well, that solid bedrock gets broken down into its basic parts. The tough quartz is left behind as sand grains. The feldspars are turned into clay. All those iron-rich minerals, they literally rust, turning into hematite. And all the other soluble stuff gets carried away by rivers to the oceans, which, by the way, is a huge reason why the sea is salty. Okay, so physical weathering has created all the cracks, and chemical weathering has turned solid rock into this weak mush of sand, clay, and rust. The mountain has been successfully sabotaged, so now it's time for the final act. It's time for the one force that never, ever stops working to take over: gravity. And this brings us right back to where we started, Caracas. Just look at this landscape. You have these unbelievably steep mountains rising right up behind the city. For millennia, these slopes have been weathered, creating this thick blanket of loose soil and weak rock. The whole area is just primed for gravity to do its thing. You can even see the scars from landslides that have happened before. This quote from our source material really gets to the heart of it. Of course, gravity always pulls straight down. We all know that. But on a slope, that force gets split. Part of the pull is actually pushing the material into the slope, kind of holding it in place. But the other part is constantly pulling it down the slope, parallel to the surface. And the only thing fighting that downhill pull is friction. So you see, a disaster like this is really a three-part recipe. First, weathering prepares the slope. It weakens the rock and turns it into soil. Second, gravity provides that constant, relentless downward pull. And third, you just need a trigger. For Caracas, that trigger was all that intense rain. It saturated the ground, which reduced the friction and added a ton of weight, until gravity finally won. And understanding this recipe is so important. It's why geologists map these danger zones and why engineers build drainage on hillsides. It's all about managing that risk before the final act begins. So a mountain doesn't just suddenly decide to fall one day. It's the final, violent chapter in a really long story of breakdown and decay, and it's all finished off by the inevitable pull of gravity. It really makes you realize the ground that seems so solid beneath our feet is always in a slow state of change, which kind of leaves us with one last big question to think about. Where will it move next?